So rate of reaction. The study of rates of chemical reaction is known as reaction kinetics. In this kind of study, we gather data from rate experiments. They tell us a lot about chemical reactions. Some of the reactions are fast, some of the reactions are slow. Not just about the speed of the reaction, we get to know a lot about mechanism of the reaction. Mechanism of the reaction is actually all about how the reactant particles reacting together, either they go to a transition state, either they form a product or a specific side product, or they form, there are intermediate steps before they get to the product stage. All of this belongs to mechanism of reaction. Now, the balanced chemical equation gives us no information about the rate of reaction. So experiments are needed to measure the rate at which the reactants are used up or products are formed, and that's how we define the word rate. Now, whenever it comes to the word rate, it means something is being divided by time. So time being the denominator is something that is pretty specific whenever we use the word rate, be it chemistry or physics. Now, so that means rate is the change in amount of reactants as they are consumed up, so they decrease, or the change in amount of products since they're made, their concentration definitely increases over time. Now, units of concentration are expressed as mole per decimeter cube. Units of times are usually expressed in seconds. So rate of reaction would be either mole per decimeter cube, and since this is divided by second, so if this goes on top, this becomes per second, or we write it as -1, -3 without this dash sign, right? So it would be like this, mole, decimeter cube inverse, and second inverse. So for slower reactions, this can be minute inverse or hour inverse. So there exist different units, but most of the time we'll be using mole per decimeter cube per second. So moving on. These are both simplest values, and they actually talk about how much of the reactant has been used up. So it's pretty easy to convert these kind of questions into mole per decimeter cube per second unit. These are for practice, baby steps. Let's get to the practical activity 9.1, which is more important. So methods for following the course of the reaction. Course of the reaction is something that is very important when it comes to rate of reaction and its measurements. So whenever we need to measure the rate of reaction with respect to time, we need a suitable method. That suitable method, by course of reaction, we mean that it is going to follow the progress of reaction. This method either measures the rate of disappearance of reactant or rate of appearance of product. There are two main types of methods, sampling and continuous. Sampling means any method that take out samples or discuss the effects in samples. That of course happens in batches. I hope when I use the word batches, you understand what that means, right? For example, your case, you are students. Every year we take a batch. This is a batch system that Cambridge or Edexcel has introduced. Every year they take a specific batch of students. Those students study, they appear an exam, and that batch is passed to or taken to the next grade. And then comes another batch and another batch. And that's how we process batches in a specific amount of time. This is what sampling means. So sampling means we process or take out a specific sample and process it after unit intervals of time. But continuous is different. Continuous means the continuity of progress of reaction or appearance or disappearance of product is taken out not over a specific after a specific interval of time, but over a period of time, continuously, of course. Hence the name continuous. So sampling. This method involves taking small samples of reaction mixture at various times, of course after regular time intervals, and then carrying out a chemical analysis on each sample. An example is the alkaline hydrolysis of bromobutane. Now, alkaline hydrolysis of bromobutane produces for us butanone and gives us bromide ions. In this case, samples are removed at various times and quenched. Quench means sudden cooling. Now, sometimes we suddenly cool the sample that we take out. It actually helps us to stop the reaction wherever it is. If the reaction is 40% complete or 60% complete or 90% complete, we stop the reaction right there and then. How do we suddenly cool something? It's pretty simple. The simplest method that we use is to add ice to it. Adding ice usually stops the reaction right then and there. Well, it's a cheaper, inexpensive method, but sometimes it also interferes by adding water to the whole system. If we don't want to do that, we can always take help of any of the techniques that relate to the use of any liquefied form of gases, such as the use of liquid nitrogen. But again, the consumption of liquid nitrogen makes it very expensive, and that is only used in a set of labs around the world. So it stops or slows down the reaction. Cooling the sample in ice is a very good example. Hydroxide ion concentration can be found by titration with a standard solution of a strong acid. Yeah, before I move on, sometimes the students tell me, why don't we put them in a fridge? Why don't we put them in a freezer? Why don't we put them in an instant fridge or freezer? Yeah, we do understand that fridges, refrigerators, freezers do cool the stuff, but they take some time to make that happen. And during the time, if we do not cool it instantly, the reaction would proceed a little bit more, and you won't be able to get the exact value for which you took the sample. So, instant cooling is actually effective, and any other method in which cooling takes time is actually ineffective. That's why put it in the fridge or the freezer is actually not going to cut it. Moving on, the hydroxide concentration can be found by titration, this one, okay, with a standard solution of a strong acid. The lesser the concentration, it means more of the reactant has been already used to form the product. The higher the concentration, the more reactant is still left over and less the reaction has been progressed. So it's pretty simple. If more acid is consumed, it means the reaction has proceeded a little. If a little less acid is consumed or lesser amount of acid is consumed, it means most of the reaction has already proceeded over to the product phase. Moving on, continues. In this method, a physical property of a reaction mixture is monitored over a period of time, and monitoring is, of course, continuous. Some examples are colorimetry, conductive multimeter, or measuring changes in gas volume or gas pressure. Now, we are going to discuss all of these in much more detail. Let's consider it. We can use a colorimeter to monitor the progress of a reaction. It measures the transmission of light through a cell containing a reaction mixture. The less concentrated the color of the reaction mixture, the more light is being transmitted through the cell. So it's pretty easy to get an idea of how much the reactants have been consumed or the product have been produced. Colorimetry is used to monitor the change in color of a particular reactant. For example, we can use this method to follow the reaction of iodine with propane. Now, in this case, propane is colorless, but iodine definitely has a color. Now, the more faded the color of the reactants are, the more iodine has already been used to process the whole reaction, which means most of the reaction has been consumed and converted into products. The darker the color is, means most of the reactants are still left over and the reaction has not proceeded much. So that's pretty easy to guess for this kind of reaction. But every time we're going through a specific type, for example, right now we are discussing colorimetry, you should be able to guess the advantages or disadvantages of it. Now, the advantages is that we're not taking a sample out. Even if we are, that is pretty easy to follow, and we're not using any chemicals, any extra chemicals for this process. The disadvantage, though, it can only be tried on colored substances. If we are completely working with colorless substances, colorimetry is not going to be an option. This is not written in the book, but the authors at this point presume that the student is capable enough of coming up with this kind of argument. If we can only use it with colored substances, what are we going to do when we are going to handle completely a set of colorless reactants and products? So yeah, there you go. I hope you can come up with a common sense based uh, points for the advantages or disadvantages of any of these options. Moving on to the next option. Now, changes in electrical conductivity of the solution can also be measured. We can use conductivity meters for this purpose, conductivity rods. For example, we can use this method to follow the reaction of trimethyl bromide or and with water, it reacts, it produces an alcohol, it produces hydrogen ions plus bromide ions. As the reaction proceeds, the electrical conductivity of the solution increases. Why? Because on the left-hand side, we have larger molecules and unionized ones that do usually will not conduct electricity better. But on the right-hand side, we have some smaller ions, such as H positive ions, which are going to be very good conductors in that case. So since ions are being formed in the reaction, this method can sometimes be used even if there are ions on both sides of the equation, because ions vary in their conductivities. For example, the small H positive and OH negative ions have very high conductivities, but since bromide ion is a bigger size ion, it has a low conductivity. So you can always try it if there are ions on one side of the equation or if there are ions on both sides of the equation. Okay. If there are ions on both sides of the equation, you can do it with the reaction, the complete reaction mixture, and you need to do it individually for the ions of this side and ions of this side at a separate place. This would give you the idea which kind of ions on which side have higher conductivity or lower conductivity. By the way, you can decide that on your own. Remember, higher charge, and this belongs to physics more than it belongs to chemistry, is equal to higher conductivity, right? And the second factor, smaller ion size, is also equal to high conductivity. So higher the charge, smaller the size, the better conductor an ion is going to be. Bigger the ion size or lesser the ion charge is going to cause it to have a low conductivity. For example, bromide ions. I hope this is clarified. And again, you can discuss the advantages or disadvantages of this reaction. If there are no ions on either side of the equation, you won't be able to use it. If there are all molecular systems on both sides of the equation, probably you won't be able to use it. So keep in mind that on the basis of common sense, you can always come up with the advantages, disadvantages, or limitations of a specific process. Moving on, the third kind, where we measure the changes in gas volume or gas pressure. For example, we can use this method to follow the reaction of benzene diazonium chloride, which is C6H5 N triple bond and positive Cl negative. Now, we can react this with water. It actually produces for us uh, the benzene-based alcohol plus nitrogen plus hydrogen chloride, actually hydrochloric acid. We can monitor the reaction by measuring the changes in volume of gas. Now, the only gas in this entire system is nitrogen gas, released with time. You may have used this method to follow the rate of reaction between calcium carbonate and hydrochloric acid. In that case, carbon dioxide gas is produced. So remember, if a gas is a part of reactants or products, only then this method can be used. So there you go, the limitations of this process. The progress of some reactions can be followed by measuring small changes in the volume of reaction mixture. For example, hydration of methyl propene, the volume decreases. Now this is methyl propene. We add water in the presence of a little amount of acid. This is also known as acidic. Actually, this is hydration, not hydrolysis. So what happens is that it produces an alcohol and it gives away the H positive ions. Now we can follow, this one is specifically for calcium carbonate reacting with hydrochloric acid. We have already understood this part back in O levels, that if a carbonate salt reacts with an acid, it produces salt plus water plus carbon dioxide. The carbon dioxide gas would be produced. Since this is airtight and is connected to a gas syringe, the plunger is going to move outwards or backwards, and the gas will be collected over here. Now, we were talking about small changes in volume of reaction mixture. An instrument called a dilatometer is used to make small changes, measure the small changes in the volume. We're talking about really small changes in this case. The temperature has to be controlled to an accuracy of a third decimal point in degree centigrade units. Before I move ahead, can you answer this question? Can you think why? Why do you think we need to control temperature to control our accuracy? Come on, any wild guesses? Any
The volume
educational
might be
guesses?
affected by the temperature.
Perfect. The volume can get affected with temperature. In case of gases, you are already familiar with the Charles law that the volume is affected by temperature in absolute units or Kelvin. You are already familiar with gases. In case of gases, so it's not just the gases. Temperature can affect other states of matter as well. For example, solids or liquids. Although that effect is very, very small. But again, the changes that we are measuring in this specific experiment are actually already really small. So yeah, the effect can be still be there, right? Usually we don't say that temperature affects the volume of liquids or solids a lot, but here where we are being accurate and we're talking about at a really small level, it is possible. Okay, so let's move on. This was just like an extension reading. You don't actually have to discuss the working of dilatometer. And in past papers, if there are a couple of questions maybe there, but they explain the whole scenario and the questions are really based upon your knowledge or common sense instead of putting you through something new. They're not going to do that. Okay? Let's move on. Calculating rate of reaction graphically. Now, rate of reaction usually changes as the reaction proceeds. This is because concentration of the reactants keep on decreasing for products keep on increasing. We are going to talk about in terms of concentration of reactants in this case, and we are going to take the isomerization of cyclopropane to propene as an example. Now, before I move any further, isomerization is actually a term in organic chemistry in which we can convert a substance into its isomer. Now, you're already familiar that isomers have the same molecular formula. So I hope you understand that this is C3H6 and this is also C3H6. Now, this is C3H6 on the basis of cycloalkanes, since this is a alkane, all singly bonded, but a cyclic compound. This is not an alkene, this is an alkene having the same general formula. This also gives you the idea that cycloalkanes and alkenes have the same general formula, CnH2n. And by the way, we have discussed this specific piece of information in the last class when we were practicing a question that some of you, I guess, live asked that question, and we practiced it for combustion and calculation of different quantitative quantities. So you probably are already familiar that both of them have the same general formula. So isomerization is the kind of reaction in organic chemistry in which we convert one isomer into another. Usually these kind of reactions are achieved under catalytic conditions, which means we might need a very good catalyst for this reaction to proceed. Now in this case, cyclopropane is being converted into propene. We can follow the progress of this reaction by measuring the decrease in concentration of cyclopropane. We can, on the other hand, keep sorry. Okay, so we can keep on working with the concentration of the product that would increase over time. So we can either measure the decrease in concentration of reactant or increase in concentration of product. The changes are considered at 500 degrees centigrade. The measurements were all made at the same temperature because the reaction rate is greatly affected by temperature. And this is the place he's already told you that the reaction rate is affected by temperature. How its reaction rate is affected by temperature for most of the reactions around the planet is something that we're going to discuss a little ahead in the same chapter. Let's continue with this. Take a look at it. You have a 5 minute interval between the time calculations, and we're starting from all the way from 0 minutes to 40 minutes. Cyclopropane concentration, as you can see, it starts from 1.5 moles per decimeter cube and decreases all the way through. On the other hand, propene at the start is of course zero since we haven't produced any product. And as we proceed, its concentration is going to increase. Now, concentration of reactants have been considered at temperature 500 degrees centigrade. Note that we put square brackets around cyclopropane and propene to indicate that the concentration units over here are mole per decimeter cube, right? These square brackets already mean that we're talking about concentration of propene. So you don't have to write the whole word concentration of propene. Just writing the name of the substance and using square brackets automatically means that we have discussed the concentration units. However, you can write the concentration units next to them just to ease out the thing that you haven't used any other unit except the standard one, or even if you have used in the units, you're already displaying them. So that's the ease, that is actually the ease of the reader right there. Now let's discuss that. On graph A is the concentration in for propene. Of course, it's an increasing graph, so it should be the graph for the product. Remember, we have already discussed in the previous chapter that the decreasing graph is the graph for reactant and increasing graph is the graph for product. Now take a look at it. We have marked all the values up till 40. And as you can see, he is actually not using dots or dots with circles around them. Instead, he's using crosses for the graph. So uh, we suggest that this is the best way to mark a point on the graph. So you should prefer it. Some students are used to draw these small bold dots. Some students are used to draw circles around them. None of this should be your preference. This one should. Okay. This point is beneficial for paper 3 and for paper 5. So all the points have already been marked for you, and how the concentration of propene changes with time in the reaction of cyclopropane to propene. The whole curve has been shown in A. Now the B part, the first part of the curve is magnified, just the first 5 minutes. We are talking about this much portion of it, I guess, about this much portion of it. Now, there are two lines, line A and line B. Line A shows the average rate over the first 5 minutes. Line B shows the actual initial rate found by drawing tangent at the start of the curve. So we will be drawing tangents at any point of the curve, and we can also go for an uh, average rate over a specific amount of time. Both the kinds of rate, instantaneous or initial rate or average rate, are discussed below. So I am keeping this diagram intentionally. I'm going to discuss a few things below, and then I'm going to come back to this diagram, and you'll understand what we are trying to say. Now, we can see from the figure 9.5b part that the concentration of propene increases from 0 to 0.27. Now, these are used for 5 minutes specifically so that we can come up with this extrapolation. So it is 0.27 mole per decimeter cube in the first 5 minutes. Okay, we can use the symbol delta, Greek symbol, to represent a change in a particular quantity. So when we are going to write it, The specific way to write it is rate of reaction equals delta concentration of protein over delta time, which means change in concentration of protein over change in time. We're not writing the whole thing. We're actually expressing them with specific symbols, hence the delta and the square bracket. This delta and square bracket means change in the concentration of. So 0.27 divided by 5, actually, that's not exactly what we are doing. What we do, and let me clarify, this is more related to mathematics. And in math, we actually take this as x2, this is x1, this is y2, this is y1. So this usually goes with y2 minus y1 over x2 minus x1. However, in this case, it's 0.27 minus 0 and 5 minus 0. Since we do not need to write minus zeros, we simply write it like this. But that doesn't mean every other value is done in the same way. These are only the first values for which we can write it like this. For every upcoming value after the first value, you're supposed to go with y2 minus y1 over x2 minus x1. That's the way we actually perform it. This is x1 actually. Okay. So in this specific case, 0.27 minus 0 and 5 minus 0, the answer comes out to be this. This gives the average rate of reaction over the first 5 minutes. You will notice, however, that the graph is a curve which becomes shallower with time, so the rate decreases with time. By measuring the change in concentration over shorter and shorter time intervals, we get an increasingly accurate value of reaction rate. If we make the time interval over which we measure the rate of reaction almost zero, we obtain a reaction rate at a particular instant. Okay, so this is important. If we go with bigger units of time, we can get a rate of reaction, but that would just be an average value. Now, average value may sometimes be misleading if you're talking about a specific single individual or a single reading. Let me clarify myself. Let's suppose there are three students in class, A, B, and C. Let's suppose their marks out of 100 every time for different students. Let's say A got 63 marks, B got 67 marks, C got a whooping 79 out of the rest. So if you're going to take an average, how would you take the average? The averages in maths are pretty simple. 63 plus 67 plus 79. I'm going to add all of them up and divide by 3. The answer would be something probably above 70, right? Can anyone please calculate it for me if you have a calculator nearby? That's 120 and 190, and 190 plus 19, that is equal to 209, probably 210. So something around 70, am I right?
Yeah,
69.6 or 7?
69.6. Yeah, yeah.
69.6 or 7. Actually 69.67 if I'm correct, right? 66667.
Yes.
Okay.
Yeah.
So for this, if you look at this value, you'd notice this value does not belong to any of these individual values. Yeah, this is an average value, but it might be misleading if we compare it with a single individual, right? So in order to get a better value than this, we need to decrease the time frame, the time interval over which the measurement is taken. The shorter the time interval is, the closer reaction rate values would be to a particular instant, right? So since we are not handling with marks, we're handling with the graph, and the graph has specific values. If I don't want to take value at this specific instant, what then? Going with an average might not work, right? This specific instance value and average value might have a difference in them, and a contradicting one at that. So what do? We go with as shorter reaction intervals over which we take the measurement as possible, almost uh, closer to zero. 1 second interval, probably less than 1 second interval. The smaller the interval is going to be, the better our results are going to be at instantaneous score. This is known as instant rate. How do we get our instant rate, we do this by drawing tangent at a particular point. Let's suppose we want to talk about this point. Let's draw a tangent right at this point. This is going to be become a triangle, and the triangle can always have a y2 value extrapolated, the y1 value extrapolated. Then a triangle always going to have an x2 value extrapolated, an x1 value extrapolated. You can always calculate. The working is the same like we have for a specific average or a larger unit of time. We still go with the y2 minus y1 and x2 minus x1. But before we do that, instead of going for a whole 4 minutes or 5 minutes, we draw a tangent. Now, it does not matter if one student takes the tangent length to be this and go with this kind of working, and the other student takes the tangent length to be this and goes with this kind of working, right? Because the answers for both the students are going to be same. Well, however, we do suggest the triangles not to be too big. In that case, you make start making mistakes. And if the triangles are too big, you can have errors over time. So try going with adequate amount of triangles when you're going to draw a tangent and go for a particular instant. This would give a much more accurate value of initial rate of reaction, or rate of reaction at any instant. Since he was talking about specifically the initial rate of reaction, which is the rate of reaction at the start of the experiment, that's why he made the argument for initial. But you don't exactly have to do it for the initial. For example, in past paper questions, he talked about this specific instant. What would you do? Okay, notice this is for 5 minutes, this is for 10 minutes, this is for 15 minutes, this is for 20 minutes. What if in exams he asks you exactly what happens at 18th minute? Of course, you will then have to draw a tangent over a system, and this is going to be extrapolated for y2, y1, x2, and x1. That's how we do it. Make sense? This should make sense to all of you because you are about to do this in paper 2, paper 3, paper 5, probably also in paper 4. The stuff we are studying right now is actually for both AS and A2. Okay, so I'm going to assume that all of you understood what I meant. So there you go. You have the average rate of reaction, and now you know instantaneous rate of reaction. Average rate of reaction is the rate of reaction for a particular period of time. Let's say 5 minutes, 3 minutes, starting 5 minutes, 5 to 10 minutes interval, 10 to 15 minutes interval, any of that. The first 30 minutes, the first 20 minutes, you can take any average, bigger or smaller. It really depends upon you. Instantaneous is the uh, rate of reaction at any instant. And since we are working graphically, you can pick any point over the whole curve for which you'd like to find the rate of reaction. And remember, for the average, we can go with the starting point and the ending point. Of course, we're going to wind up in drawing a triangle and with marking the values, of course. Here he has been extrapolating it, and but I have been discussing the triangle like this one. So yeah, this one, this one, this one, that's how. Okay. So the triangles are going to be same for the average and the instantaneous, but in average, you start with a tangent. In instantaneous, sorry, you start with a tangent. In average, you don't. That's the difference right there. Let's go for a work example. Figure 9.6 show how to draw a tangent and calculate the rate at a particular point on a curve. In this case, we're going to use the graph of concentration of cyclopropane against time. This time, they're going to go for a reactant curve. As you can see, it's a decreasing curve. So this should give you the idea right there and then that we are talking about the reactant, and reactant in this case for isomerization reaction was cyclopropane. So all 40 minutes, the slope at 10th minute gives the rate of loss of cyclopropane 10 minutes after the start. So draw the tangent and find it out. You can draw the tangent, you can always work with it. Remember, it's going to give you an x2, an x1, and y2, and y1, and you can always work with it. But this is going to be a little bit different since uh, in the case of reactant, if you're going to go with y2 minus y1, your answers might come out to be negative. So do not worry. For reactants, the answers are usually in negatives. For products, the answers are usually in positive. Why? The products have an increasing graph and the reactants have a decreasing graph. This is something pretty natural. So the rate of reaction at a given time can be found by drawing a tangent and measuring the gradient. Select the point on the graph corresponding to a particular time, 10 minutes in this example. Draw a straight line at that point that it just touches the line. The two angles between the straight line and the curve should look very similar. I think this is a pretty easy point. Extend the tangent to meet both axes. This is actually an easier way for drawing a triangle and actually an error-free way to draw a triangle too. Now, calculate the gradient or slope of the tangent. It's the similar way y2 minus y1, x minus x1. However, since our time is given in minutes, we might need to convert it into seconds at this point. So multiplication with 60, and it really gives you the value in mole per decimeter cube per second with negative. Negative represents, this is for reactants. Now, note we converted the time in from minutes to seconds by multiplying with 60. The sign of gradient is negative because the reactant concentration is decreasing, which means for increasing concentration, we'll have positive values. For decreasing concentration, we're going to have negative values. The value of minus 6.67 10 raised to the power minus 4 mole per decimeter cube per second refers to rate of change of cyclopropane or reactant's concentration. This is the rate of reaction when cyclopropane concentration is 1 mole per decimeter cube. Okay, so this was so far the idea of how to take out average or instantaneous rate of reaction. And let's discuss the changes in rate as the reaction proceeds. Now, since with the precision of the reaction, procession of the reaction, the concentration of cyclopropane keeps falling, keeps changing, we can find the rate at different concentrations, but we need to draw different tangents at several points on the graph. So in figure 9.7, we're going to show how this is done for cyclopropane concentrations, 1.5 mole per decimeter cube initial rate, 1 mole, and 0.5 mole per decimeter cube. So there you go. 1.5 mole per decimeter cube, 1 mole per decimeter cube, and 0.5 mole per decimeter cube. So you'll notice there are arrows marked. This was 1.5 mole per decimeter cube. So a tangent, this one is drawn. This arrow represents exactly 1 mole per decimeter cube. And of course, we have this tangent for this one. This arrow represents actually 0.5. So we have this tangent for this one. Now, rate at concentration, 1.5 mole per decimeter cube. The answers have been calculated. This for 1 mole, this for 0.5 moles, this. Let's move to the table below. Cyclopropane's concentration in mole per decimeter cube, the rate calculated, and then we divided the rate by cyclopropane. We divided the rate with time in seconds. Okay. So what do you think is happening over here? Why do you think we are dividing the rate by the time? Cyclopropane's concentration per second. Actually, this one, not per time. Okay. Since, as you can see, these values are similar, we are actually dividing both of these on a purpose. They can be different, both of them are, but if we divide them both, we see we're getting a constant. Now, this is going to give you a very good idea when we're going to move ahead and talk about its formulating this. Okay, so take a look. Cyclopropane's concentration at 1.5, the rate, and when we divide both, the answer is this, and this for 1, and this for 0.5. Now, a graph of rate of reaction against concentration of cyclopropane shows us that the rate is directly proportional to concentration of cyclopropane. So if the concentration of cyclopropane is doubled, the rate of reaction is doubled. If the concentration of cyclopropane falls by one third, the rate of reaction falls by one third. So there you have concentration on x-axis and the rate of decrease of cyclopropane, which is actually 10 raised to power minus 3 mole per decimeter cube per second, is given over here. So the value 0.33, 0.67, and 1 actually conforms, giving us a straight line. This is this shows how the gradient rate per over concentration is constant because the answers to the gradient are going to be constant. Actually, that's the reason we divide. This line right here for figure 9.8 gives us the idea why do we do that. Make sense? To get the point?
Yes, sir.
Yes, sir.
Okay. Um, I'm a little bit unsure whether you get my point or not, so I am going to relate it to a previous chapter of ours. In chapter number 5, we were discussing states of matter, and we were putting away different laws for gases, ideal gases though, and we were discussing how different quantities like volume, like pressure, like temperature actually affected one another. And I am going to tell you how we can use those laws, and I'm going to use those laws actually to explain the point I'm trying to make over here. Now, I hope you remember we had Boyle's law over there, not by the name of the scientist, but just to let you know what the law was. Volume of a gas is inversely proportional to its pressure at constant temperature and for a given mass of a gas, of course. Now, you know if we increase the pressure, the volume decreases, and the volume increases when there was low pressure. Now, if I change this equation and take this factor right onto this side, we can have this. Okay, let me make myself clear. So let's say we have a piston in which we're putting pressure. The pressure is P and the volume here is V. When I increase the pressure somewhat in the same piston, let's say I converted the pressure to P, the V became half P by 2. And when I actually increased it to 3P, the V became V by 3. So if I take these values, this tells us PV is equal to 1, 2P multiplied by V over 2 is equal to 1, right? And or is equal to PV, and 3P over multiplied by V is equal to 3, and you can cut it out and again 1. This is what we have been talking about. So the values actually change in such a way that they conform one another, and actually multiplying or dividing them at the same time is giving us a constant. This was multiplication rule because these are indirectly proportional. The division rule comes if I talk about the example of Charles' law over here. P directly proportional to T, so P over T is equal to a constant, right? Makes sense? That's why it's division. For directly proportional value, this kind of principle comes. That's the point I'm trying to make over here. Since they directly conform one another, the concentration in mole per decimeter cube and the rate, that's why dividing them, just like we did back in Charles' law, actually I'm gonna bring it all up here. So since they're directly proportional to one another, and it's mentioned right here, if the rate of reaction is doubled, concentration is doubled. If the rate of reaction falls by one third, concentration is going to fall by one third. If we divide both the values which are directly proportional to one another, the answers come out to be constant, and these are those constant answers after the division. This is a specific step that we usually do with physics as well as in physical chemistry. because both relate to one another. That's why this kind of division has been done. And remember, you are going to see this kind of division in past papers as well. That's why I've been emphasizing for it. Okay, let's move on. I think I've made my point clear. Let's move on to practical activity 9.2. Now, the reaction between calcium carbonate and hydrochloric acid, we understand this is a reaction which produces a gas, and the gas can always be collected in a gas syringe. So, by collecting data and then analyzing it, we can work out the relationship between the rate of reaction and concentration of reactant in this case. So, in this specific case, we're going to use the apparatus for collection of gases to collect the data about the reaction between marble chips, calcium carbonate, and hydrochloric acid. Remember, the marble chips are in excess. Okay, so set up the apparatus as shown in the figure 9.9, but remove the spot stopper from the flask and set the syringe to 0. Now, put about 10 grams of large marble chips into the flask. Each marble chip should be about the same size and weigh around the same. So it can be around 1.5 to 1.8 grams. Since for a fair reaction, we are keeping every factor that can disturb the fairness of the reaction. We're trying to keep that constant or keep the change to a very much constrained variable. All right. So putting 20 cubic centimeter of acid in the flask and leaving it for 2 seconds for the solution to become saturated with carbon dioxide. Now put the stopper on the flask and immediately start a stop clock. Record the volume of the gas in the syringe every 30 seconds until there is no further change in volume. Since the reaction would start and start producing gas and the gas would be start getting collected, we keep on measuring it until there is no further change. Now record your results in a table with these headings, the time separately, the volume of gas per cubic centimeter, final volume of gas minus volume of the gas at any time, any chosen time. Now, the hydrochloric acid is the limiting reactant. As the reaction proceeds, the concentration of hydrochloric acid decreases. Vf minus Vt, which is also given over here, right? Vt is actually volume of gas at any time. Vf is final volume of gas. It's proportional to the concentration of hydrochloric acid at each time, right? So plot a graph of Vf minus Vt against time t. Look at its shape. This will give us information about the kinetics of reaction. Why are they doing something like this? This is very much similar to paper 3. You can get questions like this in paper 3. Actually, they have been a part of past papers. One of your questions in such a way that they tell you every step of the procedure and then they want you to perform it. So that's what they are trying to get you familiarized with. If the whole experiment like this is written and you actually perform it, that's the point. And after the performance of the reaction, can you actually record all the readings and observations that they asked? And further on process, if you need, it needs to make a graph or it needs any formulas to be applied, can you apply those formulas and can you draw a graph? Then this is what this is all about. Okay. This is kinetics of the reaction, chapter 22. Well, that's not a part of AS, so I'm really not jumping over to that point. And